Very good morning to all of you. The subject title is Engineering Metallurgy and Material Testing. Objective is to impart knowledge on the phase structure of metals or alloys, the heat treatment process employed for various materials, the classification of ferrous and non-ferrous alloys, practical exposure towards microstructure of engineering materials, mechanical testing tools for engineering materials. Unit 1 deals with solid solution, substitutionals and interstitials, compound phase diagram, classification, phase reaction with an example, isomorphous, eutectoid, peritectoid, iron and iron carbon diagram. So Unit 2 deals with the heat treatment processes. So heat treatment is nothing but you are heating a particular material or alloy to a particular temperature and then you are slowly cooling to get the desired properties, in which we have full stress relief, recrystallization and spheroidizing, annealing, normalizing, hardening and tempering of steel, phase transformation, isothermal transformation, diagram for eutectoid steel, cooling curves, critical cooling rate, hardenability, Jominian quench test, ash tempering, Moore tempering, case hardening, carburizing, nitriding, cyaniding, carbonitriding, flame and induction hardening. Unit 3 deals with ferrous alloys, classification, properties, microstructure, processing and applications of low, medium, high carbon steel, flake graphite, SG iron, white, malleable cast iron, the effect of alloying elements on steel. For example, you take chromium, molybdenum, vanadium, titanium, nickel and tungsten, stainless steel and tool steels, and high-speed, low-strength alloy steels, maraging steels, die steel, wear of metals, and specification. Unit 4 deals with non-ferrous alloys, properties, composition, application, copper and its alloys, brass, bronze and cupronickel, aluminum and its alloys, duralumin, bearing alloys, nickel and titanium base alloys, metals for low and high temperature applications, Bureau of Indian Standard specifications. Unit 5 deals with mechanical testing and characterization, mechanical properties, stress strain curve for ferrous and non-ferrous alloys, mechanism of plastic deformation, slip, twinning, fracture, types, griff theory, material testing, tensile, compression and shear loads, honest test, Brunel, Rockwell and Vickers, impact test, Izod and Charpy, fatigue and creep test, fracture and toughness test, characterization techniques, scanning electron microscope, X-ray, diffractometry. Course outcomes. So at the end of the course, students will be able to know the phase reactions of various metals and alloys, have great exposure in the heat treatment processes and know their purpose in engineering applications, have knowledge in the classification, properties and applications of various ferrous alloys, know the classification and application of various non-ferrous alloy materials, identify the various mechanical properties for the ferrous and non-ferrous alloys using modern testing facilities. Textbook Jindal, Material Science and Metallurgy, Selvakumar, Engineering Metallurgy. Reference books Raghavan, Material Science and Engineering, William Callister, Material Science and Engineering. So we have e-resources like NPTEL. So you can go through the NPTEL website and thereby you can have online lectures also from the reputed IIT professors. So basically, the alloy is a substance that has metallic properties and is composed of two or more chemical elements of which at least one is metal. An alloy system contains all the alloys that can be formed by several elements in all possible proportions. If the system is made up of two elements, it is called a binary alloy system, three elements, ternary alloy system, etc. In the alloy, the constituents and elements do not retain their original properties after mixing, whereas in a composition, the forming composite retain their original properties. So that is a basic difference between alloy and composites. In a solid state, there are three possible phases. One is pure metal, compound or intermetallic alloy phase, and solid solution. Pure metal, all metals show a definite melting or freezing point. Whenever you refer the graph, in the y-axis we have temperature, in the x-axis we have a represented cooling curve for a pure metal. If the cooling curve is plotted for a pure metal, it will show the melting point or freezing point are shown in the figure. Compounds. In many binary alloy systems, when the chemical affinity of elements is great, their mutual solubility becomes limited, and compounds, also called intermediate phases, are formed rather than the solid solutions. When compound is formed, the elements lose their individual identity and characteristics properties to a large extent. Water is composed of elements that are normally gases at room temperature, yet the compound is liquid at room temperature. The compound is having its own characteristic physical, mechanical, and chemical properties. Solution is a homogeneous mixture composed of two or more substances. In such a mixture, a solute is a substance dissolved in another substance known as a solvent. The solvent is a chemical substance and can be in a solid, liquid or gaseous state. The solution can exist in gaseous, liquid or solid state. For example, if you take a simple salt or sugar which you are immersing in water, so the water is termed as solvent, whereas the salt or sugar is termed as solute. So whenever you mix, so you are getting the solution. So we have solid solution. The amount of solute that may be dissolved by a solvent is generally a function of temperature with pressure constant and usually increases with increasing temperature. So in the y-axis we have temperature in terms of Fahrenheit. In the x-axis we have time. So you're heating more than 940 degrees centigrade, and you are keeping it in a liquid state and you are slowly cooling. So the small dendrites formed, and further cooling it becomes solid, particularly at room temperature it becomes completely solid. For example, if you take a casting manufacturing process in the foundry industry, the different metals are melted in a furnace which is kept at a very high temperature. For example, if you take a grey cast iron, the temperature is nearly 1450 degrees centigrade, and the liquid metal is taken from the furnace. It will be poured into the ladle. From the ladle, it will be transferred into mold cavity. As you all know that whatever may be the shape of the casting required, the same shape available in the mold cavity. Whenever you pour the liquid metal, it slowly becomes solid. So you are starting the temperature, pouring temperature at 1450 degrees centigrade, and slowly it becomes hard. Nearly 750 to 800 degrees centigrade, it becomes solid, but it is at very red hot condition. So you cannot take the casting immediately at that particular temperature. So you're keeping for minimum 4 hours so that it completely becomes solid and it attains the room temperature, and then you can take the casting from the mold. A solid solution is formed when two metals are completely soluble in solid state and also completely soluble in solid state. In other words, when homogeneous mixture of two or more kinds of atoms occur in the solid state, they are known as solid solutions. The more abundant atomic form is referred as solvent and the less abundant atomic form is referred as solute. For example, silver 92.5% and the remainder is copper. That is, in the sterling silver, 92.5% silver and the remainder is copper, is a solid solution of silver and copper. Similarly, if you take a brass, so we have 64% copper and 36% zinc. Types of solid solutions: substitutional solid solution, ordered substitutional solid solution, disordered substitutional solid solution, and second one is interstitial solid solution. So substitutional solid solutions: if the atoms of the solvent or parent metal are replaced in the crystal lattice by atoms of solute metal, then the solid solution is known as substitutional solid solution. For example, copper atoms may substitute for nickel atoms without disturbing the FCC face-centered cubic structure of nickel. In the substitutional solid solution, the substitution can be either disordered or ordered. If we refer the sketch 5.1b, disordered substitutional solid solution, here the solute atoms have substituted disorderly for the solvent atoms on the lattice side, whereas in the 5.1c shows on ordered substitutional solid solution. Here the solute atoms are placed in a orderly manner. So you can see that here we have substitutional solid solutions. In between the gap the atoms are placed, whereas disorder on the atoms are placed in the disorder, whereas in the order kept in a specific order. The name itself you can define. Hume wrote three rules for formation of substitutional solid solution. So by studying number of alloy system, Hume wrote three formulated certain rules which govern the formation of substitutional solid solutions. These are solid solutions: solute atoms copper, solvent atoms nickel. Solvent atoms form a substitutional solid solution, a disordered substitutional or ordered substitutional solid solution. If you take the crystal structure factor, for complete solubility, the two elements should have the same type of crystal structure. Both elements should have either face-centered cubic or body-centered cubic or hexagonal-centered packaged structure. So similarly, the relative size factor, as the atomic radius difference between two elements increases, the solid solubility becomes more restricted. So it should be less than 15%. Similarly, we have chemical affinity factor and relative valence factor. So this particular sketch indicates interstitial solid solution. So the black color indicates the solvent atoms and the pink color indicates solute atoms. These are formed when atoms of small atomic radii fit into the spaces or interstitials of the lattice structure of the larger solvent atoms as shown in figure. Since the spaces of the lattice structure are restricted in size, only with small radius less than 1 angstrom are likely to form interstitial solid solution. These are hydrogen, boron, carbon, nitrogen and oxygen. So coming to the phase diagram, which covers the introduction, solubility, limits, phases, phase equilibrium, interpretation of phase diagram, binary isomorph systems, development of microstructure, mechanical properties, binary eutectic systems, development of eutectic alloy microstructure. So we have components. The elements or compounds that are mixed initially, for example, aluminum and copper. A phase is a homogeneous, physically distinct and mechanically separable portion of the material with a given chemical composition and structure. For example, you take a sketch, beta the lighter phase and alpha is a darker phase. So we have aluminum as well as copper alloy. So solubility limit solution, solid, liquid or gas solution in a single phase, mixture more than one phase. For example, you take maximum concentration for which only a single phase solution exists. So this blue color indicates the solubility limit. The y-axis we have temperature in terms of degree centigrade. In the x-axis indicates the composition. So we have taken the example of sugar with water. So whenever you add sugar in water, slowly sugar immersed. What is the solubility limit for sugar in water at 20 degrees centigrade? So you draw the perpendicular, horizontal line. See at 20 degrees centigrade, 65 percentage greater than, then it is called syrup. If it is less than 65 percentage, this is syrup plus sugar. So this is called the solubility limit. So this particular line indicates that in the left side the sugar completely immersed, that is called a solution. Beyond that, if you add more percentage of sugar, so it will have a liquid as well as solid phase, two phase. A system is at equilibrium at its free energy is at a minimum given specified time, combination of temperature, pressure and composition. The macroscopic characteristics of the system do not change with time. The system is stable. A change in temperature, pressure or composition for the system will result in an increase in the free energy and possible changes to another state whereby free energy is lowered. So if, for example, if you take one component phase diagram, the y-axis we have taken pressure, the x-axis we have temperature. So at 0 degree centigrade or less than 0 degree, we have solid ice. Whenever you increase the temperature, it becomes liquid or water. Similarly, if you increase the temperature more than 100 degrees centigrade, it becomes steam. So phase diagram indicates phases of as a function of temperature, composition and pressure. Focus on binary system, two components. We have two independent variables, one is temperature and composition. Always you are maintaining pressure as 1 atmosphere. The y-axis we have taken temperature in terms of degree centigrade, whereas in the x-axis we have taken the composition. This indicates a copper nickel systems. So we have liquid as well as solid as line. In between we have liquid plus solid. So once if you heat uh, the copper and nickel alloy more than that particular liquid as line, then naturally it comes a liquid state. Similarly, if you cool down below the solid as line, it becomes solid solution. Two phases we have liquid as well as alpha FCC solid solution. The three different phase fields liquid, liquid plus alpha, then pure alpha. Effect of temperature and composition. Changing temperature can change number of phases. For example, you take we have A FCC solid solution, we have B completely liquid. So we have D, that is in between solid as well as liquid as line. So rule 1, determination of phases present. If we know temperature and composition, then we know how many phases and which phases are present. For example, you take this particular case, in the y-axis we have temperature in terms of degree centigrade, and in the x-axis we have composition. So melting point of copper is 1085 degrees centigrade, whereas nickel is 1453 degrees centigrade. This is copper nickel phase diagram. So for example, if you take temperature 1100 degrees centigrade at composition 60 percentage, we have single phase, that is alpha. Whereas if you refer the phase, B, point B, we have two phases. That is, the point is the temperature is 1250 degrees centigrade here. So here the 1250 degrees centigrade and at 35 percentage of composition. So here we have liquid plus alpha. Yes, this is called solid solution. So here we have solid as temperature where alloy is completely solid above this line. So for example, you take a liquidous line where alloy is completely liquid. So rule number 2, if you know the temperature and composition, then we know the composition of each phase. For example, if you take the temperature at 1320 degrees centigrade, you see this particular point TA 1020 degrees centigrade, only liquid is present. So this is only liquid, whereas the composition is 35 percentage. At temperature D, only solid is present, whereas the composition is 35 percentage of nickel. Whereas at particular point temperature 1250, that is this particular point B, you refer here, both alpha as well as liquid present. That is Cl liquid 32 percentage of weight nickel, whereas 43 percentage of weight percentage of nickel. So in this way you can able to find out the composition of phases. So from this we can able to find out weight percentage of liquid as well as solid. Similarly, if you take equilibrium cooling of a copper nickel alloy, so at particularly point A, so we have at point A, you see here completely liquid. So at point B, slowly the solid becomes, whereas in the point C, you have a solid as well as liquid solution. So here majority you have a solid. Whenever you take E, it is completely 100% solid. The development of microstructure during the non-equilibrium solidification of 35% of nickel and 65% of copper alloy outcome, segregation, non-uniform distribution of elements within grains, weaker grain boundaries if alloy is reheated. So microstructure in metal alloys. Microstructure is characterized by the number of phases, their proportions and the way they are arranged. Microstructure depends on alloying elements, concentration, heat treatment, temperature, time, rate of cooling rate. Eutectic or eutectic mixture is a mixture of two or more phases at a composition that has the lowest melting point. It is where the phases simultaneously crystallize from molten solution. The proper ratios of phases to obtain eutectic is identified by the eutectic point on a binary phase diagram. The term comes from the Greek eutectos meaning easily melted. The phase diagram displays a simple binary system composed of two components A and B which has a eutectic point. The phase diagram plots relative concentration of A and B along the x-axis and temperature along the y-axis. The eutectic point is the point where the liquid phase borders directly on the solid alpha plus beta phase. It represents the minimum melting temperature of any possible alloy. The temperature that corresponds to this particular point is known as eutectic temperature. So the eutectic basic definition is the liquid transforms into two solid phases. It is liquid transforms into two solid phase alpha and beta. Eutectoid, you have one solid phase transforms into two other solid phases. Peritectic, a liquid and one solid phase transforms to a second solid phase. So pure iron when heated experiences two changes in crystal structure before it melts. At room temperature, the stable form ferrite alpha ion has a BCC crystal structure. Ferrite experiences a polymorphic transformation to FCC austenite at 912 degrees centigrade. At 1394 degrees centigrade, austenite reverts back to BCC phase delta ferrite and melts at 1538 degrees centigrade. Iron carbide called as cementite or Fe3C on intermediate compound is formed at 6.78%. Typically all steels and cast irons having carbon contents less than 6.78% of carbon. Carbon is an interstitial impurity in iron and forms a solid solution in alpha delta phases. So this is particularly iron carbon diagram in which we have in the y-axis we have temperature and the x-axis we have composition, weight percentage of carbon. So these are all the various phase structures. So we have maximum 1538 degrees centigrade. So slowly you are cooling the temperature up to we are maintaining at 400 degrees centigrade. So in this way, whenever you reduce the temperature, then there are four solid phases occurs: alpha ferrite, solid solution of carbon in iron, which indicates a BCC structure. Carbon only slightly soluble in the matrix. Maximum solubility of 0.02% at 723 degrees centigrade. So here the temperature as well as carbon percentage is important, whereas 0.008% of carbon at room temperature. Whereas if you take austenite, solid solution of carbon in delta ion FCC structure can accommodate more carbon than ferrite. Maximum of 2.08 carbon at 1148 degrees centigrade decreases to 0.8% carbon at 723 degrees centigrade. Difference in carbon solid solubility between alpha and gamma is a base for hardening of most metals. Ferrite solid solution of carbon in delta ion BCC structure, maximum solubility being 0.09% at nearly 1490 degrees centigrade. Cementite, so it is a Fe3C compound, so it's a very hard substance. Iron carbide forms when the solubility limit of carbon in alpha ferrite exceeded at room temperature below 727 degrees centigrade. Mechanically, cementite is very hard and brittle. For ferrous alloys, there are three basic types based on carbon content: iron, steel, and cast iron. So, coming to this iron, ferrite phase, steel we have 0.08 to 2.14% of carbon, whereas cast iron 2.14 to 6.7% carbon.